Hello everyone. Today we are going to discuss the most important theorem, the fundamental theorem of algebra. The statement of fundamental theorem of algebra is any polynomial p of z is equal to a0 plus a1z plus a2z square plus so on plus an z to the power of n, where an is not equal to 0 of degree n, where n is greater than or equal to 1, has at least one zero. That is, there exists at least one point z naught such that p of z naught is equal to 0. What is the statement? Every polynomial of degree n has at least one zero. That is, there exists at least one point z naught. If I substitute that point, it becomes 0. We are going to prove by using the contradiction. So what we have to prove, there exists at least one zero for the polynomial. Let us assume that p of z has no zeros in the entire complex plane. That is, p of z never becomes 0 for any z. For any z. Consider f of z as 1 by p of z on C. Here clearly, what is the singularities of f of z? That is roots of p of z, the denominator. Since p of z has no zeros, therefore it has no singularity. It means f of z is analytic in the entire complex plane. Therefore f of z is entire function. Then f of z is an entire function. Now let us take this one as equation number 1. Since what is p of z in the given in the statement? a0 plus a1z plus a2z square plus so on plus an minus 1 z to the power of n minus 1 plus an z to the power of n. From this I am going to take z to the power of n common. What you will get? a0 by z to the power of n plus a1 by z to the power of n minus 1 z will comes in the denominator. Similarly, a2 by z to the power of n minus 2 plus so on, and this one becomes an minus 1 by z plus an into z to the power of n. Therefore p of z is equal to w plus an into z to the power of n. Equation number 2. What is w? W is this one. W is this one, where what is w? W is equal to a0 by z to the power of n plus a1 by z to the power of n minus 1 plus so on plus an minus 1 by z. Clearly w tends to 0 as z tends to infinity. As z tends to infinity, This one becomes 0, 0, all terms become 0, therefore w tends to 0. Therefore, from the definition of limits at points at infinity, that is, for each epsilon is equal to modulus of an by 2, which is greater than 0. Modulus is an is not equal to 0 clearly in the statement, then modulus of an is greater than 0 by 2 is also greater than 0. There exists a radius r greater than 0 such that modulus of w minus 0 is less than epsilon for all modulus of z greater than r, from the definition of limits at infinity. Let us take this one as equation number 3. Equation number 3. For modulus of z greater than r, that is this region, modulus of an plus w, this one can be written as modulus of an minus modulus of w, which is strictly greater than, this one can be written as which is greater than or equal to modulus of an minus modulus of w. What is modulus of w is less than this one. From equation number 3, in this region, this one is less than this one, but here is minus. Multiply minus on both sides. Minus of modulus of w is greater than, this one is greater than modulus of an minus modulus of an by 2, which is equal to modulus of an minus modulus of an by 2 is modulus of an by 2. Therefore, for modulus of z greater than r, how I got this one? By equation number 3. Modulus of p of z. What is p of z by equation number 2? Modulus of w plus an into modulus of z to the power of n. Here it is this one. But in modulus of z greater than r, what we got? Modulus of an plus w is strictly greater than, this part is strictly greater than modulus of an by 2, and modulus of z is greater than r to the power of n power n. Therefore, now cross multiply. 2 by modulus of an into r to the power of n is greater than 1 by modulus of p of z for all modulus of z greater than r. But what is f of z? 1 by p of z. From equation number 1, 1 by this one can be written as, this implies modulus of f of z is less than 2 by modulus of an into r to the power of n for modulus of z greater than r. Let us take this one as equation number 4. And how I got this? By equation number 1. Now, since f of z is an entire function, since f of z is an entire function, what is the definition of entire function? A function which is analytic in the entire complex plane, then it is said to be an entire function. Every analytic function, what is the definition of analytic function? A function which is differentiable everywhere, then we say to be analytic. Every differentiable function is continuous. This implies the given function f of z is continuous everywhere. If it is continuous everywhere, then I can say that f of z is continuous on modulus of z less than or equal to r also. If any function is continuous in a closed region, therefore it is bounded. That is, there exists capital M greater than 0 such that modulus of f of z is less than or equal to capital M for modulus of z less than or equal to r. Let us take equation number 5. Take capital M naught as maximum of m comma 2 by modulus of a n to the power of r to the power of n. Then from equation number 4 and 5, by 4 and 5 we get modulus of f of z is less than or equal to capital M naught for all z. If this z belongs modulus of z less than or equal to r, then it is less than or equal to m. If it is belongs to this one, therefore it is less than or equal to m. Therefore, whatever the maximum it may be, the modulus of f of z is less than or equal to m naught for all the points. Maximum is which is bigger according to that. Therefore, what we got, f of z is an entire function as well as bounded function. Bounded entire function. Therefore, by Liouville theorem, what the Liouville theorem says, every bounded entire function is constant. Therefore, f of z is a constant function. F of z is a constant function. If f of z is a constant, that is 1 by p of z is constant. This implies p of z is a constant function. A contradiction. Why contradiction? In the statement clearly given that n is greater than or equal to 1, means at least n is 1, means at least there is one variable z. Therefore, it is, since p of z is a non-constant polynomial, hence our assumption that is p of z has no zeros is wrong. Therefore, p of z has a 0, at least one 0, a 0 in C. Have at least 1 0 in C. Now let us prove another corollary. Every polynomial equation, that is p of z is equal to a naught plus a1z plus a2z square plus so on plus anz to the power of n. This one is said to be a polynomial. If I make equal to 0, this one becomes an polynomial equation where n is greater than or equal to 1 and an is not equal to 0, has exactly n zeros. Has exactly n zeros. How many degrees is there? What is the degree of the polynomial equation? That many zeros are there. Not less than that, not more than that. Proof. By the fundamental theorem of algebra, just now we have proved. What we got? P of z is equal to 0 has at least 1 0. Say that 0 is alpha 1. Then P of alpha 1 becomes 0. Because alpha 1 I took as a 0 of p of z. Now, P of z can be written as P of z minus 0. In place of 0 I am writing P of alpha 1 because P of alpha 1 is 0. This implies, which is equal to, what is P of z? A naught plus a1z plus a2z square plus so on an z to the power of n minus, now substitute alpha 1 in the given polynomial equation, that is a naught plus a1 alpha 1 plus a2 alpha square plus so on plus an alpha 1 to the power of n. A naught get cancelled. What you will get? A1 into z minus alpha 1 plus a2 into z square minus alpha 1 square plus so on plus an into z to the power of n minus alpha 1 to the power of n. From all this, what I can take common? Z minus alpha 1 as a common. Here we will get z plus alpha 1, so on. Then remaining will be P1 of z, where what P1 of z is? P1 of z is a polynomial of degree. Out of n degree, one z is here, then the remaining will be n minus 1. Again, what the fundamental theorem of algebra says, this is the polynomial of degree n minus 1. This has at least one 0. Again, by fundamental theorem of algebra, P1 of z has at least one 0. Say that 0 will be alpha 2. Then P1 of alpha 2 becomes 0. In the same process, again what you will get? Therefore, P of z can be written as z minus alpha 1. From P1 of z, what I can take outside? Z minus alpha 2 into P2 of z. What is P2 of z? Where P2 of z is a polynomial of degree n minus 2. Continuing in this way, we have P of z is equal to 0 has exactly n zeros. Thank you.